Hey guys, how you doing? Welcome back to fourth episode of January Daily Lead Code Challenge. And today we are back with another problem of the daily challenge that we're solving in the year 2021. So today's problem is based on linked lists, and the problem statement is merge two sorted lists. And this is a very common interview problem. And this is kind of a very conceptual question, and that's why it's very much asked in many companies. And it's not very difficult. It's like not part of trees or graphs. It's just linked list, and most companies expect you even at a fresher level to know linked list. That's like a basic. So make sure you solve this problem very well and understand how to solve this problem in the most optimal manner. So without further delay, let us jump into the problem statement. And the problem statement goes like this. So we are given two sorted lists and they are linked lists. Okay. So I won't go to the definition of a linked list. Just make sure if you don't know this, just Google the definition of singly linked list, doubly linked list, circular linked lists. Okay, so these are singly linked lists and there are two sorted linked lists. So the values are in sorted manner and each are individually sorted. So there is this first list, which is 1, 2, 4, and there is the second list called 1, 3, second list containing 1, 3, 4. So as you can see, they are sorted. Basically, you need to merge these two lists such that the resultant list is also sorted. The what you can do is if they were arrays, what you could have done is put all of them together and then sort it, but that would give a bad time complexity, right? So you have to think of an approach which is optimal and kind of ex- kind of helps us get the result as well. Basically, we want a total complete linked list, which is the combination of both of these linked lists. So if there are n1 elements in the first linked list and if there are n2 elements in the second linked list, the final resultant linked list would have n1 plus n2 elements, and all the elements would be in a sorted fashion. That's what we want to achieve. So without further delay, you can just pause the video here and think about the solution because I'll be jumping to a whiteboard and discuss the solution. So jumping to the whiteboard, guys, if you want to pause the video, you can pause it here. Okay, guys. So jumping to the explanation, we will take an example. So let's take because the problem statement is very simple. We have understood what we want to achieve. Let us take an example. Let's take linked list 1 as 1, 3, 4. And we know that this is the null node, or we can denote it like this, or there are different notations. So, and this is the second linked list, 1, 2, 4. Okay. So we want to merge these two linked lists. So such that the resultant is something like 1, 1, 2, 3, 4, and 4. So the 1 comes from here and here, these two ones. The 3 comes from here, the 2 comes from here, and this 2, 4 comes from here and here. Okay, so we have understood what we want to achieve. Now the idea is how do we kind of approach this problem? How do we optimally solve this problem? The fun thing about linked list is that it's just like rewiring. So just imagine if you could somehow rewire these connections, if you could somehow rewire, we can achieve the solution we want, right? So what if, let me just rewire this stuff. Let me just say that 1 and 1 both are here. So let me just disconnect this one and connect this wire from here to here. Okay. Now this one will be from here to here as usual. From 2, I'll disconnect this one and I'll connect here to here. Similarly, from 3 to 4, I'll let it be. And from 4 to 4, I'll let it be from here to here. And I'll disconnect this one. So if you follow the red arrow now, if you start the linked list from here, you're traversing 1, 1, 2, 3, 4, and 4, and then end of the linked list. So if we can just somehow rearrange the nodes, rewire the nodes, we can sort that. And it would not take more than big of what? It would not take more than big of n1 plus n2. where n1 is the length of the first linked list, n2 is the length of the second linked list. So this is the most optimal solution, and this is the only solution that you should think about. But there is another solution actually. There is a recursive solution. We'll check how to do both of these. First of all, let us see how we can approach this solution, how we can solve this solution. So we'll see the pseudocode. Okay. So let's create a very simple dummy node. Okay, let's call this a dummy node. And this node will point to nothing. This is like a dummy node in the memory. Now we have these two linked lists 1, 3, 4 and 1, 2, 4, right? Now I already have pointers L1 and L2 pointing to these. I'll just compare L1 and L2. So basically if L1 dot value is less than or equals to L2 dot value, then what do I need to do? I just need to connect. So I have a pointer pointing to my dummy, right? I just need to connect pointer dot next equals to L1. Why? Because I need to uh, kind of connect my next value to the point to the so the smaller value comes first. Now, why is that? I'm showing you that one also. Okay, so you have dummy as this, right? So let's forget code for a while. Let's forget the code for a while. We'll go and check the code later on. So we have the smaller, which is the smaller one out of these two. We see that both of these have the same values. 1 and 1 have the same values. So you connect the first one. So dummy dot next becomes L1, that is 1, right? Dummy dot next becomes 1. This one comes here, okay? Now L1 moves from here and L1 points to the next one. So L1 points to this one. I'm just moving L1 because that is already processed. Now I'm comparing this one and this one, L1 and L2. Which one is smaller? L2 is smaller. So you connect L2 and you move L2 to here. Okay. Now you again keep on comparing like L1 and L2, which is smaller? L2 is smaller. So you connect 2 here and move L2. Now you compare again L1 and L2, which is smaller? 3 is smaller, L1 is smaller. So you connect 3 here. So this notation does not matter, okay? So I'm just denoting because of lack of space. And so 3 and 4. Now when L2 comes here, we are moving L2, L1 here. So now both of them are same. You can take L1, and once this has reached the end of the list, we'll just take the remaining part of L2 and add it to the list. And remember to add the null node. So end of linked list is always denoted by this null. So that's it. That's a very simple process, and the time complexity would be big of what, n1 plus n2, the total length of both the lists. So summation of the lengths of the two lists. There is actually a recursive solution to this problem also, and I'll discuss that because it's quite interesting. And the above solution, it's very common. Interviewers ask this a lot, but the recursive solution is generally not that much asked, but it can be a bit tricky to reach that. Or maybe we should just discuss all the solutions, right? It's very simple also. So in recursion, what happens? See, so we have this list 1, 2, 3, and we have, let's say, 1, 4, 6. Okay, now let's consider this one as L1, L2. We have already considered that, right? What if L1 dot value is less than or equals to L2 dot value? If that is the condition, and if this is the function that we are if this is the problem that we are trying to solve, so is that L1 and L2 we are passing. If L1 is less than L2 or less than or equals to L2, we can already say that this problem is already solved, and we can solve this much problem only and this much problem only. So what basically happens is L1 dot next because this one I know that this value has already been visited. It's already going to stay in this place. So L1 dot next would be the recursive call of L1 dot next, because I'll be checking from for the remaining list, and L2. Similarly, if L1 dot value is greater than L2 dot value, in this case, it's something like this. So this exactly this condition. So see, L1 dot value is greater than L2 dot value. So I know that this one will be in this position, and I can solve for the rest and append it to the main list. So I can say that L2 dot next, whatever is the solution of till L2, so L2 will be there. L2 dot next, you give me the solution of the remaining part of the problem, L1 and L2 dot next. So I am basically delegating the remaining part of the job to this recursive calls. So I am saying L1 dot next, till L1 I have solved, give me the rest part by solving this and assign it to next of this. L2 I know, give me the next part of this, solve this part and assign it to the next of this. That's it, nothing much. And you finally return L1 here and return L2 here. That's it. So what would be the base case for this recursive approach? The base case is very simple. If we reach L1 to null, or null, however you want to represent it. If L1 is null, then you return L2, because you have reached the end of one node, right? And what happens when you reach the end of one node? So you have reached end of this. Okay, let's say we are moving together. If we have reached end of this, so you just need to append the remaining part of whatever is there. That's it, right? So return L2, and similarly, if L2 is null, return L1. That's it. And if both of them are null, you will obviously return null. So that is the explanation of the recursive solution. So I think by now we have understood both of the solutions, the recursive one, this is the recursive one, and this is the iterative solution. Okay. So what you understood is, from the iterative solution, we are not using any extra space, but from the recursive solution, we use the stack space. That's all. So I kind of personally prefer the iterative solution. In terms of memory, iterative solutions are always good. But we just try to explore the solution, just so that, just so that in case of an interview, if we want to solve it, you know how to solve it. So let us jump to the code, and I will try to code it in both the ways, the recursive approach and the iterative approach. So without further delay, let's jump to the code. Yes, guys, back to the code. So this is the editor. So let us first discuss the iterative approach, or let us first discuss the iterative approach, and then we'll go to the recursive one. So for the iterative approach, as we discussed, we'll need a dummy pointer, and the dummy pointer will be nothing but, let's say, another list node. I'm using Python. You can use any language. This is completely language agnostic algorithms that we are discussing here, and you can solve it in any language of preference. So we need a pointer to this dummy node, and this will point to dummy. Okay. So while we have both L1 and L2, we'll just keep on checking, if, as we discuss, if L1 dot value is less than equals to L2 dot value, then what we'll do, we'll assign ptr dot next, the pointer dot next, to L1, and L1 goes to the next position. Okay, very simple. Do you guys want me to increase the font size? I'll try to. Okay, it's already, I guess, the maximum. Yeah, okay. So okay, let me just zoom in so that it's a bit easier for you guys to look into the code. Yeah, I hope this is better. And okay, so what is the else other condition? So else, otherwise we know, like, L1 is greater than L2 value, right? So ptr dot next will assign L2 to this one. So this is the other value, right? And finally, we'll just assign L2 to this, and then L2 equals to L2 dot next, right? And finally, once we are done with this, we'll increment PTR because we need to move the pointer, right? And finally, we'll just check if L1 is there, if any more L1 is there, if L1 is not null basically, or let's say if L1, then PTR dot next would be pointed to L1. And if L2 is there, otherwise, if either of these conditions will happen, right? Because we have an AND condition here, so both of them will not happen. So if this or that, then PTR dot next is equals to L2, right? That's it. That's it. And we just return dummy dot next. Why dummy dot next? Because dummy was a dummy pointer. We don't consider that inside our problem. We were just marking that value. So dummy dot next is the first value of our final linked list. So let us try submitting the solution. Yes, we are getting the expected solution. Now let us submit it. Yes, it's getting accepted, guys, and this is very much what the solution that we are looking for. But I'll also be discussing the recursive solution. So let us jump to the recursive solution. I'll remove this code from here because the recursive solution will also need some space, and don't want to make it a bit look clumsy. So first we write the base cases. So if not L1, and there's a very common Python syntax. So if not L1 is similar to like if L1 is equals to none. Okay. So if L1 is not equals to null, then we return L2. And if L2 is equals to none, then you return L1. Okay. Otherwise, we have the base case. So you just check if L1 dot value, similarly, like previously we did, L1 dot value is less than L2 dot value. Then you just assign the next one to this. L1 dot next is equals to uh, self dot merge to. So this is a recursive call, right? L1 dot next, because L1 is already solved, L2 and return L1, right? And otherwise, that is basically else L2 dot next is equals to self dot merge to lists L1 and L2 dot next, right? And finally you return L2 here. So that should solve the problems. Let us just try submitting this. That's the recursive solution, guys. And we are getting the expected solution. Let us try submitting this. Yep, this one is also getting accepted. So I hope you guys understood both the solutions, and do let us know in the comment section which one you guys would prefer out of these two. I think both of them are pretty easy, but go ahead, whichever you like. And I hope the videos are very useful to you guys. So do consider sharing, liking, subscribing to the channel. And that's it. That's it for today. See you next time in another coding challenge, maybe tomorrow to the next January challenge of daily challenge. That's it. That's it for today. Thank you so much for watching.